let's finally start. It is my pleasure to introduce Hernán Grecco today for our LIBREhub seminar. So very relevant to our topic of how to push Latin America with open source hardware instrumentation that we can build. Instrumentation always comes with software to control it. And Hernán is one of maybe even the Latin American software expert for software control of instrumentation. And so it's a big pleasure to have him here today. There are just fewer method and instrumentation developers in Latin America compared to other continents. So it's really great to have all the community merging here at the LIBREhub seminar. He's a physicist in Argentina, and yeah, I think the rest I will just let you take away yourself in your slides. So thank you very much for joining us today, Hernán.
Hi, Tobias. Good morning, everybody, and thanks for the invitation. So thanks for the invitation. As Tobias was mentioning, my name is Hernán Grecco, and today I want to talk to you about how we can keep up with the growing complexity in our experiments, and how can open tools help us to do that. The seminar is going to be in English, but if you would like to ask questions, feel free to do it also you can do it in Spanish. And so today we will explore a little bit what is the line between software and hardware and how this is disappearing, and how in modern experiments we need to depend on this software to orchestrate complex procedures. I will share a little bit of my experience building open source software and also building open source experimental devices. So let me briefly tell you a little bit about my lab, which is located in the University of Buenos Aires, here in Argentina. So we are mostly a lab devoted to the interface between physics, biology, and data science. What we are interested in is to understand the three-dimensional organization of living matter. And for this, many times we don't have the tools to measure what we need to measure to do this. Therefore, we develop optical methods to quantify molecular processes and statistical methods to put together complex and diverse experimental data sets. Within this circle, this virtuous circle, many times some tools that we develop spare the interest of other people. So for example, we have developed Visa, which is the Python standard to communicate with instruments. We have also interacted with a company, YPF, which develops works with petrol in Argentina. It's a main petrol company, to develop a microscopy settings. We develop a microscope, which I will talk to you today. We have also worked with Satellogic, which is a satellite company, working with them to develop a hyperspectral camera. And closing the circle, by the way, some of my students are now creating this company called Node Visa, which is a way to have commercially supported Visa connectivity with instruments in a modern and asynchronously aware, concurrent manner. And I think that today is a bright moment for science. We are witnesses an extraordinary scientific breakthroughs from black holes to gravitational waves, the Higgs boson detections, mRNA vaccines, gene editing, and whole specimen imaging, and much more that you can sure think of more. But to achieve these fantastic things, measurements are getting more sophisticated. And consider, for example, the progression for very simple experimental setups to the integrated technologies that we have today. For example, in 1899, Ramón y Cajal revealed the hidden structure of the brain by a simple staining techniques. 100 years to the future, today we can color and trace individual neurons, mapping the brain in a stunning detail. But this sophistication has a price, which is complexity. To see how far we have come, we can also compare two pivotal experiments in physics. In the late 1800s, the electron, which was the first subatomic particle to be discovered, was done using a simple gas tube, the Crookes tube. It took a small setup to unlock this amazing discovery. 100 years to the future, and fast forward to 2011, the discovery of this Higgs boson requires now the Large Hadron Collider, which is this 27-kilometer ring, which is underground, in which thousands of scientists and engineers with cutting-edge technology are able to splash particles into one another and discover the mysteries of matter. Also, as experiments become more complex, the amount of data that we generate has exploded. And for example, in the 1700s, Olaf Römer made 140 very careful measurements of Jupiter's moons. And with this, he was the first one to measure the speed of light. And with a reasonably good estimate, by the way. But now in 2019, to image the black hole requires 5 million gigabytes of data and a global network of telescopes. The scale of the data has changed a lot. And this has allowed us also to pursue much more complex and larger scientific questions. And turning that data into knowledge, it's also a challenge of its own. And our analysis pipelines are much more complex. This is one of my favorite historical experiments from the Argentinian physicist Gaviola while working in Germany. He measured the molecular fluorescent lifetime using basic tools and math, which I can explain to you in 15 minutes. It's very simple, very elegant, and effective. Nowadays, for example, in 2015, detecting gravitational waves require pushing the technology and the analysis to limits that are able to measure distortions smaller than an atom. And all this requires sophisticated experiments, massive data sets, complex analysis, and a global collection of people working together that share in tools and trust. And the only way to achieve that is via open principles. What we do should be accessible, transparent, rigorous, reproducible, replicable. And to achieve that, we need to have protocols, data, software, hardware, metadata, and manuscripts that can be shared among scientists. And today, I'm going to focus on how we can share software, and not just software, but software for instrumentation. Because software is everywhere. Every single thing that we have around us is powered by software. Even cameras, they have embedded software inside. Of course, our cell phones, the television, every single device has software, even if we think it's just hardware. Because the boundary between software and hardware is blurring. So it used to be that we have hardware on one side, electronics, and software on another side, like the code that you write and is compiled to work on those electronics. But nowadays, it actually looks more like this. Yeah. If you think of Arduino microcontrollers, FPGAs, they are programmable, they are adaptable, and they are increasingly defined by the software that runs on them. We cannot build today a platform of hardware without thinking also in the software, as Tobias was mentioning in the introduction. And also, we require software to control different experiments. Yeah, most instruments today, they are not just about a single instrument. It's more like an orchestration of different devices working together to produce the data, right? The same way like an orchestra, different musicians work together to produce fantastic music. So we need to have a way to talk to all those instruments. We need to have a way to put our own software into that hardware. We need to have a way to produce a software that can measure in our experiments. If we do that correctly, we win a great battle, because the software to control instruments would be like a protocol, not a protocol that we follow, but a protocol that the computer follows, and therefore makes experiments much more reproducible, auditable, and we can have a good log of everything that has happened. So let's tell a little bit why I went into this. And actually, it all goes back to around 2001. I was working at the University of Buenos Aires between my undergrad thesis and starting my PhD. And we had this scanning tunneling microscope that was a very old device with a control via HPIV, which is, let's say, a version of GPIV for those of you who know about this. And it was running a software written in HP Basics, Hewlett Packard Basic, which was talking to the instruments and saying what are the instructions that you need to do. that computer was dying, and we need to migrate that software into something new. Therefore, what we did at that moment is, because we have the source code of the software, and we were also to put a sniffer here, the HPAV cable, we're able to rewrite the whole software using LabVIEW, which is the national instrument tool to build instruments. That was great. And some of the things that I want to mention is the company at that moment gave us the source material. Therefore, we were able to rewrite the software once that the company stopped supporting that computer. And therefore, the instrument, which was really good quality, we were able to bring 10 or 15 years to the future and continue operational. Fast forward a few years, I started to work in Dortmund as a postdoc at the Max Planck Instrument for molecular physiology. And over there, my first job was to build a device to do a screening using a microscope. So basically, this is a lab tech chamber, and if you see, there are small spots, which are like 384 of them. In each you have cells, and you can move from spot to spot and take images. And this was taking just standard images of fluorescence, transmission, fluorescent lifetime images as well. And that process was taking like maybe 30 or 40 hours, something like that, right? And I kept working on that software, and the software was kind of a mess because it contained an acquisition software that I built using LabVIEW, 8.2 at that moment. Then it has an analysis code written in MATLAB and optimized certain aspects in C. And then there was an exploration tool written also that I wrote in MATLAB and Java. And it was really, really annoying having to maintain these three code bases in 3 different languages. And also on top of that, the Max Planck has a very strict VPN at that moment in the institute. And therefore, in order to know the status of the microscope from outside the lab, I built a chatbot using Gmail chat in that moment that was telling me what was the status, how many hours was still missing, and so on and so forth. So I decided to do something with this, which was basically try to generate a single unified code base to do all these things, and at the same time reduce the time of acquisition of the whole microscope, which I took from something between 30 and 40 hours to less than 15. Okay, and the missing part to be able to achieve that, when I started to analyze the ecosystem, I realized that Python, which already in 2007 was looking at the future to be language of science, programming language of science, there were really good libraries to do data analysis. NumPy was there, SciPy was there. Yes, it was difficult to install. Yes, you had to compile from sources, but it was there. There was a lot of tools starting to appear for data exploration, although not as good as before. But there was very little to do acquisition and data and instrument orchestration with Python. And therefore, I decided to start working on that, and I built PyVisa. PyVisa, as I mentioned before, is the default software to control instruments from Python. And the way it worked is that you already have a few libraries which are called Visa libraries from different vendors like National Instruments, Agilent, Keysight, and many more, right? And PyVisa is providing a front end to those vendors. This is the front end, and it contains a main backend, which is this PyVisa NI, which talks to the C library, and then it contains another backend, which is a pure Python version of this backend. This was this is very useful for hardware in which this hardware library is not available. And I also created a simulation library. By the way, when I started to work in PyVisa, there was already a small, very tiny package from Python that was basically just doing the C library bindings to PyVisa, to NIVisa. And therefore, when I took over, I talked to the developer. I said, look, I really would like to spend time on this. These are my ideas. And this person was very kind and also very open to give me the project so I could push it forward. And the current state of PyVisa is thanks to that generosity of the original person that developed the C bindings, and then the work that I put on top of that. And by the way, a little bit of the history of that is called that. And that's some of the good practices that you can always discuss when you talk about open source software. And I also developed LANS, which is a platform on top of PyVisa to simplify instrument control. And basically, what you do is you can talk to any of these instruments, like a signal generator or oscilloscope, via any of these ports, like Ethernet, USB, serial, GPIB, and many more. And it's really simple. You just import the package. You create what is called a resource manager, which is a list of all the devices which are connected to your computer, and then you open that resource using the address, and then you just send a message. Right? By the way, when I a few years after developing PyVisa, I realized that I didn't have the bandwidth to continue developing PyVisa, and therefore I scouted for people in the community that were making wonderful contribution. But those persons was at PhD students that I think was working in France, Matthew Laya. I didn't know him personally, but he was doing great contribution to PyVisa, and he's currently the PyVisa maintainer, right? And that's another thing that I want to mention. Open source requires building a community and trusting the community, right? And realizing that once that you build that community, it's not just your project, but it's a community project. So, by the way, a few things that we did with PyVisa, for example, this is our light sheet fluorescent microscope. It's called CRUSA. It's a joint development between my lab and a group of students of the Faculty of Industrial Design. And basically, that whole thing is controlled from Python. This is the user interface. I'm not going to show you the code, but the user interface has a part that you can select the excitation and the emission channel, the sample position. You can generate if you want to do a time lapse, or you want to do a scanning set in time or set in channels. You can generate all of this. You have the image here, and you are saving the data as you go. So all this is controlled for Python. So it's that orchestrates all sorts of devices: a camera, the lasers, the light blockers, the stage to move the sample, to rotate the sample, and so on and so forth. And so this a little bit shows the power that you can build in your own tools from scratch. And the good thing is that now you don't need to build everything from scratch, because all that information is open source, and therefore you can get that tool that I have built and develop your own. And I would like to tell you one more story, which is, as I did maybe 20 or 25 years ago with that scanning targeting microscope, something very similar happened not so far ago. Like 2 or 3 years ago, we wanted to do some very long measurements of spectroscopic measurements. And we have this spectrofluorimeter, which is a Horiba Igon very nice spectrofluorimeter with an excitation arm, an emission arm, monochromators, everything. The optics is great, the mechanics is great, the detectors are great. But the problem of that device is that it's controlled with a very, very old electronics using Windows 95, and the data has to be saved in a 3¼ inch disk. Yeah, for those of you who are very young, this is not the save button. This is actually a place in which you were storing your data to transfer to another computer. So that device that we have in our School of Science was having this type of very old electronics and very old software. But the device was great. So what we did is we rebuilt the electronics. This is our demo with open source electronics, and we create an open source software that runs on a Jupyter notebook that is able to do the same measurements that we were doing before, but now with a software and a hardware that we can maintain and keep using, and we don't depend on a very old computer and a very old file format. Yeah. By the way, here there was no information given by the company about the code, so we have to reverse engineer everything, right? And I would argue that one of the very important thing that we need to learn from the open hardware movement is that we need to be able to access the inner workings of the devices if we're working in a lab, because we want to be able to tweak it, to maintain it, and to keep using it. And not only we were able to redo measurements that they were done before, but also we gave them new tools to this device. For example, we generated a way of characterizing a conversion nanoparticles, which are nanoparticles in which, for example, they are built from helium and ytterbium. You excite with infrared light, and they emit visible light. That type of measurement was not possible in the original instrument, but because we were able to change the original instrument, we were able to add more capabilities. The same thing with lifetime. We did time resolved fluorescent measurements. So now we put a pulse laser, and the software is able to generate a sequence of laser pulses and do a time-dependent detection, and therefore measure the fluorescence as a function of time, and from those be able to measure the emission lifetimes of those nanoparticles. So as you see, being able to develop your own software is great because it allows you to first give new life to all devices, allows you to add new capabilities to all devices. But I would argue that also allows you to have more control of your experiments, because you can now program the protocol that you actually need, which might be different to the one that the vendor gave you, right? And so I want to give you some final thoughts on that, and then I'm open to questions. First is that instrumentation is hard because it's everything that is hard about software plus everything that is hard about hardware. And sadly, instrumentation is not taught so much in the universities. I think we need to do more for this. Sharing instruments is hard because there's a lot of diversity in the hardware. So if I build a software to simulate, I don't know, like a random walk, I give you that software to you, and it will run in your computer very likely. But if I give you a software to control a specific instrument, if you don't have the exact same hardware, it will be very difficult for you to adapt. Therefore, we need to incorporate into our development better techniques that allow us to build modular software and therefore be able to exchange more software. There has been funding for data analysis and funding for simulation software, but there has not been so much funding for instrumentation software. And I think that is a pity, because if you don't have good data, then it doesn't matter how good the data analysis is. If you have good data, it doesn't matter how good your simulations are to simulate nature conditions. What you want is good data, and to generate good data, you need good instruments and good instrumentation software. And if we need to start funding the generation of open source hardware and open source software. And we need to start rewarding the people who do this, right? And it's very nice to see that there are some now initiatives and foundations that give money to this type of things. It's also very nice to see that several journals are starting to publish papers devoted to open source software and hardware for instrumentation. And I think we need to do more, because the way that the instruments are the way in which we acquire data, and we need to keep that to the highest standard possible. Having reproducible outcome requires having a reproducible protocols, and we can do that through good software. So with that, I thank you again for your interest and for your attention.
Muchas gracias, Hernán.
No, gracias a vos, Tobias, por la invitación. Siempre un gusto.